Good afternoon. My name is Miles Biggs. I'm giving a presentation on centrifugal pumps, the design, performance, and applications. So to get started off with an introduction, the operating principle behind centrifugal pumps uses rotational energy, typically from an electric motor, to move fluids through the conversion of kinetic energy into pressure. The fluid enters the pump impeller along or near the rotating axis and is accelerated outward by centrifugal force. Applications commonly used in water supply systems, wastewater processing, industrial processes, chemical processing, and HVAC systems. And this is due to their ability to handle large volumes of fluid efficiently. Advantages: simple design, low maintenance, smooth flow output, and the ability to handle high flow rates with relatively low pressure. Classification of centrifugal pumps. So you have, based on flow type, you're going to have radial, axial, and mixed flow pumps based on the number of stages, which a single stage is going to be one impeller and multi-stage is going to be multiple impellers. And then casing designs, you have volute and diffuser pumps as your main two. Design and key components. The impeller is the rotating component that imparts the kinetic energy to the fluid. Your casing is the outer shell that houses the impeller and directs the flow of the fluid. The shaft connects the impeller to the motor and transmits the rotational energy. And then you have your bearings that support the shaft and reduces friction during rotation. Then you have your seal box, which prevents leakage of the pump fluid along the shaft. And then your suction and discharge nozzles are your entry and exit points for the fluid being pumped. So for impellers, this is going to be the key component for centrifugal pumps. It's designed to transfer the energy from the motor to the fluid, and increases its velocity and pressure. So your types of impellers, main types of impellers are going to be open impeller. That's going to be on the left in the photo, which is going to be the vanes are not enclosed, making it suitable for handling larger solids or debris that's within your fluid, or your semi-open impeller, which is a balance between open and enclosed, offering improved performance and debris handling. And then closed impeller, the vanes are going to be completely enclosed within a protective shroud, providing better efficiency and higher pressure. So your casings. So the casing is the outer structure that surrounds the impeller, directing the fluid flow into and out of the pump. It helps contain the pressure and directs the flow in an efficient manner. Your types of casings. So for a volute casing, a spiral shaped casing that gradually increases in area, helping to convert kinetic energy into pressure. This is common in single stage pumps. A diffuser casing contains fixed vanes that help slow down the fluid and convert kinetic energy into pressure, improving the efficiency in multi stage pumps. You have a split casing, which features a two-piece design for easy access and maintenance, often used in large, high-capacity pumps. And then a cylindrical casing, which is a simple, more compact design, often used in smaller pumps with moderate capacities. So this is an example of a volute casing design. As you can see, where the fluid comes out through the impeller, it's smaller in area, and as it gradually reaches your outlet, it's a larger area. So another type of casing, this is a close coupled in casing. And in this design, the casing is designed as either volute or semi-volute to efficiently direct the fluid flow into the impeller and then out through the discharge. The key characteristics of these casings include it's a compact single piece construction, so it's directly attached to the motor, eliminating the need for separate bearing frames and couplings. And then it has an axial suction and radial discharge. So the fluid enters axially and exits at a 90-degree angle, optimizing hydraulic efficiency. The flow ranges for smaller pumps is going to be from 5 to 100 gallons per minute. Large pumps is going to be 1,500 to 5,000 gallons per minute. The end suction pump casing is going to be designed as a single or double volute casings, and this is designed to guide the fluid efficiently from the suction inlet into the impeller and then out through the discharge. So some of your key characteristics of the end suction casing is going to be the single volute design is going to be in your smaller pumps and using standard end suction pumps, simple and efficient guidance to create radial thrust imbalances at high flow rates. But yeah, it can create radial thrust imbalances at high flow rates. Then your double volute design is going to be used in larger pumps, and it includes a second volute chamber to balance pressure and reduce radial forces on the impeller, and it's used in higher capacities. And it also has an axial suction and radial discharge. The flow ranges for small pumps is about the same as the previous casing. Horizontal split casings. So this is going to be a casing that's split along the horizontal center line, and it's an axial split design, and it has a double suction impeller. And it has balanced hydraulic performance. And this means that the double volute casing minimizes radial thrust, extending bearing and seal life. And the flow ranges for medium pumps about 500 to 5,000 gallons per minute. Large pumps is 5,000 to 50,000 plus gallons per minute. Vertical split casings, they're split perpendicular to the shaft rather than along the shaft center line. These pumps are designed for high pressure and high temperature applications, often found in industries such as oil and gas, power plants, and chemical processing. It's a radial split casing, so the pump casing is divided into two halves vertically, making it ideal for high pressure operations. The inline impeller arrangement, typically, these pumps are going to be multi-stage with impellers stacked vertically to generate higher pressures. And then the high pressure capability, um, it's able to handle extreme conditions like boiler feed water and pipeline applications. Flow ranges are going to depend on the number of designs and the impeller design as well. So for our performance characteristics, we're going to have the flow versus head curve. So the relationship between flow rate and head, flow increases, head decreases. Then you have your BEP, which is your best efficiency point. It's the optimal point for efficiency, balancing the flow, head, and power. This is where you're going to want to run your pump and how you're going to pick your pump. Your flow rate is the volume of fluid moved per unit of time, gallons per minute. And then your NPSH, which is your net positive suction head, which is going to be the minimum pressure required at suction to prevent cavitation. And then your power consumption is going to be the energy required to operate the pump. So for a pump curve, you have your flow rate is on your x-axis, your y-axis is going to be your head. And then for pump performance line, it shows how head decreases as flow increases, typically a downward slope. Your best efficiency point is going to be the point where the system curve and your pump curve come together, and that's where you're going to want to operate your pump at. And then selecting a pump is where you're going to use this BEP to select your pump. So this is a series pump curve. This whenever you're going to have pumps in series, centrifugal pumps in series, and it's going to be used to overcome larger system head loss than one pump can handle alone. For two identical pumps in series, the head will be twice the head of a single pump at the same flow rate, as indicated with 0.2. But in practice, it's actually going to move along the system curve to 0.3. And so that's where you're going to want to run your pump if you have two operating in series. And then 0.1 is where you would have one pump running. So your parallel pump curve, the axes are the same, but parallel pumps are used to overcome larger volume flows than one pump can handle alone. And so for two identical pumps in parallel and the head kept constant, the flow rate doubles compared to a single pump as indicated with 0.2. Note though that in practice, it's actually going to move along the system curve line to 0.3. And so that's where you would be running two pumps in parallel. And so a system curve. So we have seen these in the past two pump curves. It's that line that's coming along the bottom. And so what that shows us is you're going to use that to select the pump. You match this with the pump curve to select your certain pump that you want. The intersection of the two determines the BEP, and it gives you the flow rate and head that you will need for your specific operating conditions. The axes are the same as the pump curve. The curve shape is typically upward sloping. As flow increases, the head required by the system also increases. So friction losses, that's what's causing the head to increase. As flow increases, the friction losses in the pipes, fittings, and valves also increase, requiring more head. And then our pump affinity laws are going to be they're mathematical relationships that describe how changes in pump speed, impeller diameter, or system characteristics affect pump performance. So our key relationships here in A is going to be flow rate is directly proportional to pump speed or impeller diameter. In B, head is proportional to the square of the speed or the diameter of the pump, and then of the impeller. And then for C, your power required is proportional to the cube of the speed or diameter of the impeller. Lastly, for our conclusion, centrifugal pumps are versatile and efficient. They're widely used for fluid movement in various industries due to their simple design and ability to handle large volumes of fluid. They're key components. It's necessary to understand these if you really want to pick the right pump and get your right efficiency and keep longevity in your equipment. Also, reliable operation. They're a crucial tool in fluid handling, offering reliability, ease of maintenance, and adaptability for diverse applications. That's it. Thank you.